Thank you very much for joining a quite heavy session on quantum threats and quantum cryptography. But I hope you'll enjoy it. So first of all, who am I? I'm Anna. I'm currently working as a Java developer advocate in the Java team at Oracle. I enjoy particularly security, Java security, and working with tools, any kind of tools. But in my daily job, I enjoy working with the JDK tools. We're going to, of course, see today Java security. We're going to see JDK tools. We're going to see Spring Boot. So it's going to be a lot of examples in this talk. Now, if you want to ask me more about this talk or about other concepts regarding Java, you can ask me and you can follow me on social media. I'm available on Blue Sky, on X, and Mastodon. I just need to tell you that on X, if you're DMing me, I don't know why I don't receive emails about those DMs. So I have to check it from time to time to really receive those. But if you have any other questions, the other social media really seems to work better in terms of connecting. So what are the goals of the talk today? First of all, understand the urgency, why quantum threats to cryptography are real and not just something in the future and just we should not think about them. Then probably recognize the risks of our encrypted data and how those work. Of course, explore solutions. And how do we do those in Java? Obviously, what tools are available to leverage those solutions? And of course, in the end, I can understand better how to build resilience against potential quantum threats in the future. And let's start with why quantum cryptography matters now, matters today. And in the app, do all of you have the Huva app, the application of the conference? Good. So in the app, I just posted a small survey asking you about how frequently do you become aware of data leakages in general, inside or outside of your organization. Sometimes it's better to be connected what others did as well. Maybe you integrate with their data. And results. Well, apparently the majority kind of hears about this monthly, which is nice. Now, second place, yearly. Weekly, very few people, and just one person hears more than once per week. You're kind of my person, more than once per week. Actually, data leakages kind of occur more than once per week, unfortunately. And to bring it to your attention, some of these, well, do any of you heard about Coinbase? So they were pretty, I heard about them because of their data breach. I didn't know about them before that, what they were doing. So pretty much this is a cryptocurrency exchange company based in the United States, has a lot of users, handles a lot of data and a lot of money. So what happened is that cyber criminals bribed their overseas customer support staff. They got access to some personal data of 97,000 users. Of course, the attackers were nice. They demanded a $20 million ransom. Coinbase refused to pay. Instead, they offered a nice reward for information leading to the perpetrators. I guess they found out who were the people. And unfortunately, the article also says that the expenses that they have to do is 180 million to 400 million for remediation costs. So this is more than their initial ransom. Something went wrong with their data. Wow, losing crypto. Encryption and losing crypto. But that was people can say yeah, but that's a human error. It's not encryption at fault. Maybe. Then, have you heard about Dior and their luxury leak? Well, they're not that concerned. They also kind of lost some personal data, but what they said is a good thing is that they haven't lost any financial data. However, personal data in the wrong hands can be used for phishing. Customer metadata is still gold, especially nowadays when AI is capable to get some calls and somebody faking to be somebody else as your provider, having all your details and asking you for more so they gain access also to your financial data. So metadata is important. And this is my story. It's a nice email that I received 5 years ago. And I'm going to tell you why it matters maybe in the present and maybe in the future. Now, 5 years ago, I got this email from a company where I bought some flights. So I usually go for my vacations. I just go for the cheapest option available. There are many portals. They seem reliable. They had a nice score on a specific app that gathers all these portals. So I trusted them with my data. I bought my ticket, and of course, when you buy your ticket, you tend to give like everything about you. When is your date of birth? When is your passport expiring? Who emitted your passport number, and all these great details about yourself. Now, in their email, they told me like, hey, we lost your data. Is it data leakage? I mean, it might be potential, but the good news is we're using industry standard cryptographic methods. So you are safe because, you know, the guys that stole this data, they cannot decipher it, unfortunately. So for them, fortunately for you. Now, we are also like making our systems secure so that we don't lose any data in the future. But if you have any questions, just contact us. Now, me 5 years ago, I was like, data is safe. Well, true, until I found out about this. Steal now, decrypt later, also known as retrospective decryption. And if you know, well, cryptography standards and algorithms and cipher suits that were applicable 5 years ago, nowadays, well, they're not all of them so good as 5 years ago because, well, there's different computation capabilities. So also the bad actors can have access to that data easier. So what steal now, decrypt later is, which is a real thing, is a strategy in which bad actors are saving currently unreadable data for a future with an expectation where they're going to be able to decrypt it. And how will they decrypt it in the future? Well, of course, when more computation power is available. But a lot of these encryption, the algorithms that we're using nowadays, they're indestructible, right? Except for quantum computers. Well, because quantum computers, they are leveraging principles of quantum mechanics to perform computations way more efficiently than the classical computers. Probably already know they're using qubits, which is pretty much a quantum bit, the equivalent of a classical bit that our computers are using. And once a quantum computer has enough qubits and also is immune to any quantum decoherence phenomenon, the Shor's quantum algorithm can factorize large integers and exponentially faster, and that would solve the discrete logarithm problem that many of our current encryption algorithms are being relied on. Of course, mathematics is at the base of our current encryption algorithms that we're using nowadays and we are enjoying. What I want to say is that such computation efficiency can break asymmetric encryption like RSA or ECC. Some people gather together in something called Cloud Security Alliance. They do some research on how to better prepare for this. And they also determined when a day when the current encryption algorithms are going to be breakable is going to come. And that is called Y2Q or Q day. That refers to this anticipated moment when quantum computers are going to be capable to break our current encryption. Now, that picture was taken like 2 or 3 days ago, so currently it's like 327 days further there. The countdown is actively working. That's what I'm trying to say on that website. And if you add the numbers there, it kind of says 2030, right? So the expectation is 2030 something. It's not that long. 2030, 2031, it's just around the corner. So in order to counteract that, we need to forward think about our security standards. Now, our current public key cryptography has its roots in 1976. Yes, since 1976, but of course it has expanded and grown. But back then, Diffie and Hellman published new directions in cryptography, and that's the fundament that we know nowadays for public key cryptography. Now, as we want to prevent the possibility to have our cryptography standards being broken, on August 14, 2024, the US National Institute of Standards and Technology, which probably you might have heard of, called NIST for short, released final versions of its 3 post-quantum quantum encryption standards. And these standards are even nowadays present and respected by the Java security and the JDK security. So the first standard relates to general encryption. So how general encryption should work. And also this standard is based on ML-Chem. We're going to use that quite a lot in this presentation. ML-Chem stands for Module Lattice-Based Key Encapsulation Mechanism. Very long. Let's call it ML-Chem. And if you wonder what is a lattice and why is it better than the rest, well, because it's a grid-like mathematical structure formed by all sets of integers and linear combinations of basis vectors and in an n-dimensional space. So what I want to say here with this complicated definition, kind of impossible to break. So even by quantum computers. So a new type of mathematics is going to be the foundation of this post-quantum cryptography. Now, these latest based CAMs are designed to resist quantum computer attacks because they are relying on more complex mathematical problems, such learning with errors or ring learning with errors, if I'm correct. But the post-quantum cryptography algorithms, while they're still based on mathematical problems and mathematical algorithms, and you might say, hey, but they are so good. Yeah, they are that good, and they are to be relied on. And they're called post-quantum cryptography algorithms. Why is post-quantum? Because we also have pre-quantum algorithms, and those are actually based on what we currently know as algorithms for our cryptography. Now, the second standard is for protecting digital signatures, because you need general encryption standard for algorithms that require for general encryption standard. The second one is for digital signatures. And that is based on MLDSA. It's modular lattice-based digital signature algorithm. So these two are going to also be present in the next part about Java. But why look into these now? Why look into these standards? Because they adopted it. I mean, you know, quantum computers are not here. Why should we care? Well, because sometimes government agencies decide that, well, you know what? We want for our computer systems to handle sensitive information and to be protected over the next decade by using these specific algorithms. So this is an excerpt from an order, like it says from 2022. It says like until 2032 or something, December 31, 2031, we kind of need to use these PQC algorithms to handle our security. You never know. And you know, if the government is making a move to go forward in adopting this, we need a way to support this within our applications. And to do that, it starts from the ground up, from Java. So that's why the JDK security has released a few things and followed NIST recommendations for post-quantum cryptography. So first of all, I introduced the key encapsulation mechanism API, because you need a new API to handle this kind of encryption that resists quantum computer attack, right? But after releasing this, and also an algorithm called Diffie-Hellman-Chem, DHChem for short, which is a pre-quantum one. That was for JDK 21, as an example. Now, in JDK 24, there are three more things that followed. Key derivation function API, also to help with enforcing these parts of resisting to quantum computer attacks, but also its own implementation of MLChem and MLDSA, the ones that we talked earlier in the standards. So pretty much implementing something to work with those standards that were, you know, mandatory. And of course, in 25, because, you know, KDF, key derivation function API, was in preview, now it become final. Now, this is pretty much a lot of theory. But how do you go towards post-quantum cryptography? What's the connection between all these three? Like, there's like very complicated words, right? So the connection and how do we adopt the standards starts with a new type of standard for public key encryption. I told you that the current public key encryption is pretty much relying on Diffie-Hellman's cryptography, right? So we need a new standard that would work for public key encryption and works with these algorithms and signatures. In this case, for HPKE, the Hybrid Public Key Encryption, this standard is for public key encryption and lets a sender to encrypt arbitrary length messages under a receiver's public key. You're going to see that in a bit. Now, what it means is actually secure communication based on asymmetric keys and can be either pre-quantum and post-quantum. So you can use both DHChem and MLChem in this case. Now, Java has adopted this layered strategy for quantum safety, like first in JDK 21 and then going to JDK 24 and JDK 25, in order to meet HPKE implementation. And this is an excerpt from the RFC there. How do you do that? How do you start as a developer? So let's look a bit in description here. So to embrace HPK in Java, you start with the CAM API, and you're pretty much going to use the key generation API that is available in Java. That's been there, key pair generator has been there for a while, nothing new. It just needs a new type of parameter for that. Now, once you have the key, you can call the key encapsulation function. It is called usually by the sender, and he's taking the receiver's public key, that's okay to be had, in possession, and output a shared secret value. Now, the shared secret value is sent over to the receiver, and only the receiver can decrypt this one and can decapsulate actually this shared key because they have the private key, obviously. If some attacker is like getting in the possession of the encapsulated shared secret, there's no problem because only the receiver can decapsulate it and look at it. So that's the advantage of using this one. Now, from a CAM shared secret, what can do in order to go forward? You can use the KDF API, also available since JDK 24, to have a series of derived keys that then you can use to encrypt your data and authenticate plain text messages between sender and receiver. So you pretty much add more layers of security to the way that you're encrypting, and then decryption is going to go on the other side. Now, KDF is doing a lot of computations, and pretty much it reads in input keying materials, and those can be like optional and can be like extract key new material or securely expand new values into large system of keys. So all this is available and implemented in Java. But on the long run, HPKE in Java has like something like this. And what is important for you to remember is that HPKE is always KDF plus CAM plus AEAD. Now, AEAD is what it means authenticated encryption with additional data. Very complicated. And I haven't talked to you about that one. There's going to be a new JEP or something. Well, apparently that one already exists in Java because the cipher, the object cipher, supports authenticated encryption with additional data already, having some standard algorithms for that one already in Java. So in between 21 and 24, that's what has been done to layer the ground for HPKE in Java. Okay, let me show you how this works, because I think there's been a lot of theory. Because there are some complex things to understand, we're going to start with a little simulation. And all the time, I'm getting my algorithms names from the Java security standard algorithm names. So what I'm going to use a simulator and talking between Alice and Bob to understand how secure communication with quantum algorithms works. So let me start my simulator. Let me just make this one. Localhost. Oh, wait. I need internet for this? No. It should work without internet. HTTP methods must be tokens, huh? Oh yes, HTTPS. Thank you. Because I usually go with HTTPS. That's true. Thanks. So we have a nice application here. I'd like to see how this works pretty much, and we're going to see how that is implemented in Java. So we're going to start with Bob. Bob is going to be the one that is going to generate the CAM key pairs. The reason is because he's the receiver of the message that Alice is going to send at some point. So what Bob does, it sends a message to Alice, and when it gets to Alice, well, in order to send this message, it needs to generate the key pair. So to generate the key pair is using ML-CAM algorithm that I said earlier that was introduced in Java, and I'm just going to keep on session my public key and private key so that the communication can go further. In real life, the public key is sent through a secure communication channel somehow to Alice. Now, after being done with this, what Alice can do, and I have a public key and a private key, what Alice can do is like encapsulate the shared secret. Let me go to Alice. And for encapsulation of the shared secret, I'm getting here, I'm going to use the CAM API that was introduced in JDK 21 to make an encapsulation of that public key. So no need to do any extras, just create an encapsulation of that key. And once the key is available, to share the key in the session. So I have run now an encapsulated CAM message, a shared key that both of them can exchange. Because I want to send a message further, and I want to make sure that that message is encrypted, I want to derive that key. So I'm going to click on derive key, and the derivation of key is using the new KDF API. Let me make this a little bit bigger. So to use the KDF API, what I'm getting is the shared key that I had with CAM, and then I'm using the new HKDF parameter spec to actually add a derivation to my existing shared secret key. And once I'm happy with that, I can set the encryption key for further encrypting my message. Now, if we're going to be going further, now everything seems more and more secure, right? So let's do another let's do a message to encrypt, hello from Spring.io, and call the encrypt message. And here's the part with authenticated encryption with additional data is coming into place because I'm using a cipher. And if you're wondering which cipher from the existing ones, from the standard names is supporting the authenticated encryption with additional data, besides the AES one, if you go here to the standard security, you just have to do this, AEAD. And that gets you to the ChaCha20 Poly 1305 type of cipher. Yes, you kind of have to provide the cipher names. These are the standard names. I'm not taking them out of the thin air and putting them in the code. I'm actually taking them from the Java security standards. But in this case, I prefer to go with AES because it's much more known standard than ChaCha20. So now I have a signature, an Alice public key, and everything. I encrypted my message. I want to sign my encrypted message, so to make sure that the person on the other side, when they get my message, will be able to get it. So let me go to the sign part. So once I get to the sign part, where's my sign? Yeah. So my signature here is I'm signing with MLDSA, and in this case, I'm using MLDSA 87. It's one of the available implementations for the MLDSA signature. And as I've seen some examples on the internet, there's no such thing as this. There's not existing in the security standards. There's only 3 of them. And if you're interested, you can just do this, MLDSA. And it says MLDSA 44, MLDSA 65, and MLDSA 87. If you're using the MLDSA simple, you have to also give the group name. Which group name of these 3 are you using for signing your digital certificate further? Let's go further. Good. On the other hand, now that I've done and sent my message and I encrypted my message, what Bob can do can decapsulate the shared secret because, well, he has the shared secret, but also he has the private key to decapsulate it. And then once it gets there, it can also verify the signature and get to the MLDSA part and do the verification, a very simple verification. Doesn't need to do anything very complicated. And then it can decrypt the message because it knows what kind of cipher instance it's using. It has the shared secret, and it can safely go and decrypt it. So if I'm just going to click decrypt, let's go on here. You can see the decrypted message was the one that I sent earlier, hello from Spring.io. Nothing hard-coded in the app or whatsoever. So this is just a small example to show you how things are working between 2 actors like Alice and Bob and how they're exchanging this data securely using the new implementations that are available since JDK 24. But let's look more closer to another application, a Spring Boot one. And I have a tic-tac-toe app on my local, but of course, it's good to use to play tic-tac-toe. Now, what makes it so special about it, unlike the other one that was starting in 8080, my game is using a bundle that has a proper key store and a trust store so that I can enable mutual authentication for my application. Nothing fancy so far, something that we've seen with our Spring Boot applications, right? So if I am to run this application, this is going to start on the other port, unlike the one that I had previously. Let me make this bigger. Localhost 443. Now, what I have done for my local application, I have generated a certificate authority certificate myself with KeyTool, which is something that you shouldn't do at home. But for the sake of the example, I've done it myself. So when I'm doing this, I'm actually needing to provide a certificate myself as a client so that I will be enabled to access the URL. Okay, I'm just going to say, let's go further for this session. Okay, and the connection failed, probably because I don't have the right certificate. And let me fix that. Just me go here. Come on. Sorry. Damn it. I need to go to settings to import my own certificate. Yeah. So I need to import a new certificate for my app. Just going to delete this one. Open it with a very secure password for my app, and hopefully it's going to go better. Okay. Come on. Yeah. Here. Okay, I need to accept again. And now I can reach my application once I provided the right certificate. Just later more to register and so on. Okay, so now I can play tic-tac-toe, all is good. Well, why would we go through all this? Because in this situation, we need a way to kind of replace the keys and how the certificates that I used here are signed, because currently I'm using the normal way of encryption, with the quantum computer one. And to show you which one I'm using, I have the TLS handshake enabled, so I'm just going to search for the server hello. Come on, yeah. For the server hello to check which key is being used. So currently I'm using a key that is using the name group of X2519, which is normal security and normal encryption that is available nowadays. Now, if I would like to up my game and improve what's going on right here, I can use KeyTool to generate for my current certificates key pairs that are using MLChem. And how to do that? I'm going to go to my setup and just explain you a little bit on how it works. So, to make this a little bit bigger. So in order to simulate what I showed you earlier, I said that I have a little script where I'm using a lot of KeyTool. So I created my own certificate authority, don't do this at home, with a key pair, and signed it, created for validity of a lot of time, 10 years. But what I can do if I'm a certificate authority of the future that I want to protect this, I could also go and have this certificate protected further if I'm using MLChem as a key algorithm for my CA. So certainly, also I need a server certificate, and then I need to sign the certificate request that I'm using on server side with that certificate authority. So for that one, just going to use KeyTool again and generate key pair normally. And in this case, I'm using it as just a regular algorithm of elliptic curve that is currently available. But I can enhance it even more to use MLChem as an algorithm and protect it even more if I'm using KeyTool to generate a key pair for that as well. So in the moment that the client side would have a certificate that is using MLChem, this key and this kind of secure communication would be preferred instead of the other one. And of course, need to register them in the certificate request and so on and so forth. Now, if I'm getting to step 4, normally, and I'm getting here because I need to extract the CA private key, if at the moment I would use the normal OpenSSL that is available on the market, it's available on our laptop, that OpenSSL that we normally have, it works with the current encryption standards. So if I would try to do that for what I have here above, for my certificate authority, for my certificate authority certificate, which I used MLChem for it, I wouldn't be able to extract that key because I don't have the right provider. There is in the works at the moment another type of provider, and let me show it to you, that is being developed by Open Quantum Safe. And this provider is actually going to be better. It's called OQS provider, Open Quantum Safe Provider for OpenSSL, that is going to help you to extract these kind of keys that are based on MLChem or that are using MLDSA, because this provider is actually capable to handle quantum cryptography resistant algorithms. The current ones that we have just pretty much general purpose ones. But also, if I'm just going to use only the server-side one, which is pretty much normal, and go to my current and regenerate my script, this should be fine. Let's see if we can observe this in Java, or we can do something with it in Java, although I don't have a client one. So just going here and go to current. Yes, setup.ch. Okay, so I'm regenerating everything, but also adding a key pair for my own application. So if I'm just going to restart this one again. Okay. And if I'm going to my browser, okay, I'm just going to go again with advanced, accept risk and continue. It fails to authenticate me because I regenerated my server-side certificate, so now I need a new one to connect. So in order to do that, I just need to go again to my import in the settings, delete my previous one because it's already called Anna, regenerate my new one, and then OK. So that should get me quite OK, and accept the new certificate. So once again, I can log in and so on. Now, at the moment, the browsers are not supporting 100% these algorithms that are post-quantum cryptography enabled. There is some research going on how that can be done in the browser. So that's why I cannot simulate this properly. But on the Java side, we can observe the quantum, the keys that we have done for the certificate and so on. So we have some ways to observe this if we're like doing only implementation in Java. And to do that, sorry about this, I have started also JFR when I started my application. So just to show you a bit, because I want to profile my application and want to capture if I really am using MLChem and so on. So what I've done, I just want to observe the SSL handshake in my logs, but also I wanted to like see in the flight records what options I have there for my application. So if I'm going to look at my generated files, just go here. I need to see which one is the newest. I think this one. So I have some events here. I'm not sure if I can make this bigger. But in the Java development kit, I captured a few events, the SSL handshake that occurred earlier, but also the details of my certificate and what kind of keys is being using. And there is one that is using the key type MLChem, the one that on the server side that I've generated right now. When we're going to move our applications from this kind of encryption that we're using right now, if you're having like this kind of certificates that are using like the both sides, it's going to be better like to have key pairs for both sides, and it's going to be smoother to transition to them. And always like to keep an eye on what you have and inspect on what types of certificates you have. You can use the events of JFR to do that. I pretty much did that in my profile by just putting them to true, and that's it. So what I wanted to say is that the helpful JDK tools that are available right now are the ones for key tool. Probably you've already known this tool for a long time. You can generate MLChem key pairs and certificates, like what I did for my own key store. And in my case, what I did, I started with generating the key pair for EC. So because I needed to sign my certificate with EC. But then I generated an MLChem key pair for that certificate signed with EC in the second part. So it was a two-part thing. I kept something from the old implementation and got to a second part of the second one. Now, Another way to work with these new algorithms is that we also support MLDSA key pairs. So do the digital signature for certificates can also be done with key tool. So it's pretty much the same thing. I could just signed in one case my existing certificate and not use EC at all, just go with MLDSA all of the way. So there are two ways to do that. We can always give like key algorithm, like and then the group name, or just give the group name directly by looking at the name in the Java security standards. Now, if you want to capture relevant details about X509 certificates, what I did and what I could do with GFR, I just enabled those details regarding the X509 certificates, put them to true, and I was able to capture that when I started GFR or when I use it like JCMD to start GFR. You can also configure GFR from the command line. You don't have to go directly to an XML and do it like this manually, but you can do also like a command from the command line. It's pretty easy. And because I talked about JCMD, if you're not profiling your application, then it's okay. You're not starting your application with the profiler enabled because it adds some overhead. Small, but it adds. And it makes sense. You should profile your application when you need it only. Then you can start to profile your application using JCMD with GFR start and just save that in a specific place. So you can also give the profile furthermore. If you don't want to like use a specific view or viewer to look into the GFR events that you have, like I use my IDE 1, but you can also use the command the GFR print to print the events that are available there and have them seen. And furthermore, if like you're really looking into why catching these events, well, because they contain information about the peer host, for example, in the SSL handshake, the protocol version that they use, and sometimes they give information about the cipher suit that they're using, and the cipher suit can give you an idea of what kind of encryption you're using for your application. Sometimes when you're profiling, you might have some sensitive data in your profile data. And to filter data in such a recording file, because that can be stored somewhere and be accepted, you can use the command of GFR scrub. So just go plainly and use that without any issue. You can like use the GFR scrub. Is pretty easy. Like put the filters to your recording file, and then there's an output file with all the previous files scrubbed of what you didn't want to have based on the filters. You can supply which events you want to include, like for file read or file write. You can also include the category of events, like ones regarding garbage collection or ones regarding TLS. Or you can remove all events by category. Like in the case, like exclude the GC category at all, or exclude anything regarding security, or anything that you might believe that from an event that should not be seen and captured. So what's next for you? The first thing is like to audit your encrypted assets and maybe look at what kind of encryption you're using right now and see what you want to do further with uploading that. Usually to make sure that you're using a proper encryption algorithm and make sure that everything works for you. If you're updating your application to a recent JDK, that is kind of taken care of based on the security policies that are in the JDK by default. So usually there are some algorithms that are being deemed as legacy, they are disabled. There's a reason for that. So go with that first. And of course, don't assume that encrypted equals safe forever. If you want to learn more, there are a few places that you can connect and learn more what's going on the security side. We're pretty much active on YouTube, so we're publishing videos, especially on security, on how CAM works. There was a video on post-quantum security and how that works in Java as well. And of course, we post articles on inside.java and dev.java. And I want to thank you for listening to me. If you have any questions, I would like to receive them now, or you can go through the application as well, if there's any question. Thank you. There's a question in Spanish, which I can read, but it takes me a while to understand. So, okay. I'll go to the one in English, and then maybe the Spanish one I can talk afterwards. Somebody asked, like, are there any specific cryptographic events that GFR can capture when using HPKE? like key generation, encryption times, or errors. GFR captures events that are specific in general to how TLS is working or how the details of security of certificates are there. So there's no need to be something special regarding the secure communication itself. By default, the events that have been there for a while, like JDK TLS handshake, they can capture events that use the new algorithms as well. We don't need to like re-implement new types of events. If there would be the case for a specific implementation that is not captured or visualized right now, probably that will be taken into account. But regarding key generation and encryption times, I don't think that would be relevant at this moment. And yeah, and I'll need to look at that. Do you have a GitHub repository with your demo project? Yes, I do. I can share that one. If you want to try it. But I thought it was like pretty trivial with the commands that I used. But if you like want to try it, I can make it available on GitHub. Thank you for the question. Okay, somebody said, can you back one more slide? Yes. Sorry for going this fast. I apologize. Okay. Should we expect a performance decrease for the post-quantum algorithms compared to RSA and NEC? Performance in terms of what? Like you think that because of this new APIs added to process the shared secret, there will be some slowness in how encryption and decryption is working? If the person is yeah. So that's. So at the moment, these APIs and implementations, what I showed here is pretty much like very simple types of using this. We're pretty much solely relying on the providers themselves to look into this. But at the moment, there is no such a report that's going to be a performance decrease because we're adding these extra APIs over. Okay, somebody asked, like, there were examples with TLS 1.3 only, how we can make it safe with TLS 1.2. Yeah, about that. The standard is kind of going towards TLS 1.3. I know that usually when you do the handshake in the browser kind of says, well, to the server, yeah, I would like minimum TLS 1.2 at the moment. But I think that at the moment this is working only with TLS 1.3. I'm not sure if they are compatible with TLS 1.2. And I know that there's in the works in the world an idea of having an open quantum safe TLS 1.3 version. So what the scientists working on these standards forward, they're looking into like upgrading the current TLS 1.3 that we have and have it quantum safe, not looking at TLS 1.2. The world is kind of stepping away from TLS 1.2. And I think that one also has like some end of date one to go away further from it. At some point, NIST must have published one of those as well. Okay. Let's see if I got all that. Okay. Oh, yeah, I'm searching. ¿Cómo se maneja? In English. How is ephemeral key management handled in high concurrency scenarios when using HPKE in Java applications? I haven't tried that. I cannot answer to that one. It's a very interesting question. It's like ephemeral key management handled high concurrent. Didn't go that far. Do you have like an example, like where you're going to be concerned about this? Like what kind of application? Like give me more examples to the situation about that. Like what would be like a high concurrency scenarios where you're like worried about how the key management is going on? If the person is in the room, of course. No. Okay, I could ask other people that are, if they have like anything related to this or they know anything related to this, but this is very high level to respond right now and to give an answer to that. Sorry. Any other question?
Is there kind of a timeline when the post-cryptography is adapted in these SSL libraries?
So at the moment, that provider is version 0.7.0. They are working to make it available, and I haven't seen a timeline, but they're like kind of working to make it on 1.0.0 because of the NIST. So the moment that the governments, in also us in EU, we have our regulatory part as well in terms of standards. When they pose a deadline, that's when the hurry up situation is going on. But I don't know anything about the roadmap. We're pretty much, Java's kind of following the roadmap that NIST gives. And for OpenSSL, probably they do the same. But I think it's in their interest to have the provider finalized. I'm also looking forward to 1.0.0. Well, if there's no other any other question, we can also catch up at lunch. Okay, yeah.
About this Y2Q date.
Yeah.
Do you think everyone's going to be ready by then?
In theory, yes. We pretty much rely on people. I mean, you can do this. We rely on people, but also on how the urgency is being inflicted by certain organisms. I mean, the one that the government was issued by the government of the United States of America is one way to do it. So when the government kind of tells you to do it, you kind of go. So it's pretty much like going from the regulatory part into like go further and adapt it. We're gonna see if like how the urgency goes. And I know that some people are believing that, yeah, I don't think that quantum computers can become a reality. I used to think the same about the RISC-V architectures a couple of years ago, and then I received an email like 2 months ago that there's some company producing their first laptops with RISC-V architectures. So nothing is impossible for us as humans. And I believe that now that we have, AI in our availability, we can like infer and have other possibility to like create even more than we did before. So I do believe that sometimes it's going to start maybe from regulatory point of view, and it's going to like kind of constrain us to go further. But I think that some organizations are going to adopt this earlier.
Okay, thanks.
You're welcome. Thank you again, everyone, and let's catch up at lunch or through the app as well. Thanks.